I am Rene Solzbacher, a student in the Surgical Robotics and Augmented Reality Lab led by Professor Hung. We have developed, built and tested a fully robotic surgical system for the removal of bone tumors. The system consists of an endoscope robot for visual feedback, a drilling robot, as well as an integrated control system. Robotic minimally invasive removal of bone tumors is possible with our system. Bone tumors, in this case unicameral bone cysts, are benign lesions that can occur in the immature skeletons of young children. Often found incidentally, they sometimes require removal. Traditionally, this is done using open surgery. An incision is made into the skin and a hole, large enough to reach the entire lesion, is cut into the bone. A selection of rigid instruments is used to scrape out the lesion, clean it, and fill it with bone graft material. The opening in the bone, also called the bone window, causes additional weakness. Reaching the entire lesion with the instruments can also be problematic. After surgery, plates and screws are necessary to fixate the bone window and add additional strength. This approach requires extensive time to heal, which negatively impacts children during their vital years of development. To overcome the inherent downsides of open surgery, our robot system is designed for minimally invasive keyhole surgery. 2 ports are created, one for the bone drilling robot and one for the endoscope robot. Our bone drilling robot uses a bendable compliant joint with a drill bit to conduct surgery. Novel wave-shaped notches give the compliant joint a high degree of rigidity while still achieving a small bending radius at a maximum bend angle of 90 degrees. Thus, accessing the entire lesion through a small port is possible. The ideal parameters for the wave-shaped notches have been determined through ANSYS finite element analysis simulations. To facilitate visual feedback during a surgery, a commercial endoscope has been adapted to be controlled robotically. Robotic controls have also been added to all functions of the body, like rotation, translation, and bending. Additionally, a diagonal quad-roller friction mechanism has been developed to precisely control the endoscope near the tip. The rollers are aligned at different angles and apply pressure to the endoscope. Using different rotation speeds, the tip can be translated and rotated. These actions will then be mirrored by the robotic parts surrounding the main body of the endoscope. In a series of preclinical trials, the performance of the surgery system was evaluated. Cow femurs were prepared with artificial bone cysts, and the surgeon performed the surgical procedure. Following successful experiments, human cadaver trials were conducted. 2 human femurs were prepared, similar to the cow femurs, and the proposed operating procedure was carried out. The evaluation included ease of use, percentage of removed cystic material, as well as adherence to surgical requirements such as sterilizability and human safety. In conclusion, we have designed and developed a flexible drilling robot and an endoscope robot based on the medical necessity for minimally invasive bone tumor removal. The system has been developed in close relationship with expert surgeons and to the exact specifications required for the operating theater. Functionality and efficiency have been validated through a series of experiments and preclinical trials. Flexibility, navigation, and ease of use are only a few of the evaluated criteria. Future development of the system will see the adaptation to different surgeries by reducing the drill diameter. This will allow application in more delicate areas such as the spine. Additionally, improvements to the control strategy are actively being developed, further increasing intuitiveness and reducing required surgeon training.